Alrighty, so we have a quick review, right? We had a combinational device. We have digital inputs and outputs that you know about. We have a functional specification, and we're sort of getting a glimpse that we can, for certain functional specifications, we can come up with these connections of PFETs and NFETs that allow us to build CMOS logic that implements that. Okay, and then the last thing we mentioned was a timing specification. How long does it take for this gate to work? And now what I want to do is to talk about that. So we have this notion is that when I change the input voltage, the output voltage doesn't change instantaneously. I have to charge and discharge the capacitance associated with this wire. It's small. It's on the order of, tens or hundreds of attofarads. Anybody remember what atto means? What's the 10 to the minus 18th farads? You can sort of say, that's not very much, Chris. And you can say, well, that's true, but then these resistors, these currents aren't very big either. They're on the order of picoamps or maybe microamps. Okay, so we're talking about microamp currents, or nanoamp currents, microamp currents, somewhere in there. Okay, charging and discharging attofarad capacitors. Okay, but it still takes time. It's all very small, but it takes time. It can take, getting signals to go across the network and to change them out of one of the logic gates might take on the order of tens of picoseconds, and then basically transmitting the signal down the wire. You can see it takes about 50 picoseconds per millimeter. In other words, the speed of light along these conductors embedded inside these dielectrics, these insulating dielectrics, is not quite the speed of light. And you can say, oh, this all seems pretty fast to me, Chris. Picoseconds, that seems fast. And the answer is yes, except you remember your chip is actually probably 20 millimeters across these days. And you're trying to design a set of logic and transmission wires that all operate within 1,000 picoseconds. And you're sort of going, whoa, a gigahertz processor. And you can sort of say, whoa, this is starting to be a challenge. So the fundamental limitations of physics, keep things from going too fast. They're not infinitely fast. Let me say something about how we measure delays. So what we have here is here's the input waveform, and here's the output waveform. If you look very closely at their picture, you can see on the input voltage axis here, Vin, I've carefully given you some dotted lines that represent the VIL and VIH voltage levels. So they mark the, so for a while this guy is below VIL, which means it's a valid zero, but as he changes, he crosses the input low threshold, goes up and eventually crosses the input high threshold. And at this point, right at this where I have the little cursor there, where that first vertical dotted line is, we can see that that's the first moment that the input switches to a valid high. And the way we're going to measure the delay of a gate is we're going to see how long it takes for the output of that gate to become a valid output low. So valid input high to valid output low. So VIH on the input to VOL on the output. We measure that time, and we measure it for all the devices, and we come up with a specification that is guaranteed to be longer than that measurement, the so-called propagation delay measurement. How long does it take for new information to propagate in? I've changed the input from a 0 to a 1, logically. How long does it take before I get in this case for an inverting piece of logic, how long does it take? This is called the propagation delay of the gate. And we have a specification such that it's guaranteed to be longer than any actual device that you buy. So if I sell you a 20 picosecond propagation delay gate, okay, what I'm telling you is if you buy all my gates and you wire them up, you will find no gate that has a propagation delay, either as the output goes from 0 to 1 or from 1 to 0, longer than 20 picoseconds. You might find some that will go in 10 picoseconds. You might find some that go at 5, but you'll never find any longer than 20 picoseconds, which was my TPD. So think of that as an upper bound in how long it takes valid inputs to be reflected as valid outputs to the gate. Everybody got that? So that's a fundamental, it hides a lot of details, but the idea is I'm coming up with a number you can use to say, I'm going to make a guess about the timing of this thing. And it's these collection of details that goes into figuring out how to build a processor that has a certain cycle time. And we'll be there in 3 or 4 weeks. Okay, there's a different sort of measurement called contamination delay. okay, which is invalid in to invalid out. In other words, how long does it take between when the input first becomes invalid? For in this case, this input crosses the VIL threshold there. It went from being a valid 0 to an invalid voltage right at this point. How long does it take for the output to become invalid? So now what we're doing is sort of measuring how, if I go from valid to invalid on the input, how long does the old good value still stick around on the output? A default assumption you can make is, if I don't tell you, always assume it's 0. Assume that the instant the inputs go bad, in other words, they're no longer valid, the output is no longer valid. So, but we do provide, in our specification, the idea of being able to tell you what that number is. And we'll actually see that in a particular case in like 3 lectures from now, where we're going to actually come back and be worried about that particular number. So we have a timing specifications where we're going to provide you with 2 numbers. Okay, how long the output stays valid after the input is changed to invalid. That's called the contamination delay. So the contamination delay is a lower bound in all those measurements. You're guaranteed that it will be good for at least that long. And the propagation delay, which is after I change the input, how long is it before the new output is guaranteed to be there? Okay, and the TPD, okay, sort of gives us information of how long you have to wait. And then after that, you're all good. Okay, now if I give you the numbers, for instance, 4 and 1 nanoseconds here, you can actually use a whole circuit here, okay, of gates, and you can say, look, I can use the TPDs and the TCDs to figure out, okay, the acyclic combinational, the TPD of that combinational circuit, that collection of gates, right? Alrighty, so TPD is the longest path from an input to the output. Looking at the TPDs of each device. What is the longest path here? If I change one of A, B, or C, what's the longest time I have to wait before Y? Yes? 12, and what you did is you looked for the longest path through the circuit and you added up the TPDs along that path. Okay? If I change the TPD of that collection, you look at all possible paths between input and output, you sum the TPDs along those paths, and you pick the largest number you find. What about TCD for this device, for this combo device? What do you have to do? Well, TCD is the minimum path, so I'm going to look for the shortest possible path and sum the TCDs. And if I do that, the shortest possible path is just 2 gates, so I get a TCD of 2 nanoseconds. Okay, I'm going to stop there.